Alright, so with this lecture we start MOSFET circuits. We'll do some DC circuits first and then we'll do AC and put it all together and make amplifiers. Uh, to begin with, one major goal which we'll keep in mind as we go through more and more circuits and various amplifier configuration is that by the end of this course, we want to design an amplifier that has a gain of about 10,000. Alright, this is our goal. This is one of the major goals of this course. And we want to design an amplifier that has two inputs and one output, an op amp, right? So we want to design an operational amplifier that has a gain of about 10,000. Alright, so we'll keep this in mind as we go along. Not right away, but in a couple of lectures, we'll keep coming back to this as we discuss various amplifier configurations. Okay, just to revise, just to kind of refresh our memories, these are the drain current equations for the NMOS. So right now, this lecture we'll talk about only NMOS circuits, maybe next one also. So saturation mu n C ox W by 2L VGS minus VT the whole squared. Saturation is defined as VGS minus VT less than or equal to VDS. And triode, etc., etc. In this lecture, the transistor will not turn off. Later on, it will turn off maybe I think after a couple of lectures. Alright. Also, we'll use these numbers kind of consistently so that we don't have to keep on inventing new numbers. So we'll use a threshold voltage of 0.4 volts for the NMOS, for the PMOS minus 0.4. Mu n Cox 200 microamp per volt squared, mu p Cox 100. We'll use W by L of the NMOS as 20, W by L of P as 40. And these are such that the product mu n Cox W by L n is 4 and this also is 4. So these are kind of, they give the same mu Cox W by L NMOS PMOS. Also VDD we'll use as 3 practically throughout this semester, I think, unless otherwise specified. So okay, so let us begin. So let us start with the simplest possible MOSFET circuit. A simplest circuit has to have one resistor, because if there is no resistor, there is no circuit, and we already know the currents and voltages from our MOSFET current equations. So we put a resistor in the drain and connect a 3 volt at top of the drain. This is of course the common source amplifier configuration. And right now we just want to learn to solve these different circuits under DC conditions. So I've put a 0.9 volt here, 3 volt here. RD is given to be 2 kilo ohms. Question is solve the circuit. And solving means find all the unknown currents and voltages. In this circuit, the unknown currents and voltages are ID and VD. Of course, once we find one, the other is directly calculatable from the Ohm's law for the resistor. Okay. So what I'd like you to do, and I'm not sure if I've said this, emphasized this before, is that as I go through these circuits, I would like you to pause the video, solve the circuit, and then continue the video. Because the way you are going to learn to solve is by solving yourself. If you just watch me solve, you are not going to solve. You're not going to learn to solve. Alright? So the best thing is to pause with each circuit, solve, and then continue. Alright? Of course, I will continue the video, but you please pause the video and solve and continue. Alright? Okay, I'm continuing. So here is of course, the first question we ask when we have MOSFET circuits is, well, I want to solve the circuit, so I have to use a MOSFET drain current equation to solve. But which drain current equation to use? Because there are at least two, if I assume the transistor to be on, triode or saturation. Which current to use? Well, the answer would be I would use the equation corresponding to whichever region the transistor is operating in. Now, in order to find what region it is operating in, I need to know the drain voltage. but the drain voltage is not known unless I solve the circuit. So how do I decide which region the transistor is operating in? I don't know actually. So here is a method that is generally used to solve MOSFET circuits. What we do is we'll assume that the transistor is in a region, particular region. We'll assume saturation. I'll tell you in a minute, half a minute, why. So we'll assume that all the transistors, if there are more than one, all the transistors are in saturation. We'll solve the circuit. So we'll use the saturation region drain current equations, solve the circuit, find all the drain voltages. Then we'll check based on these drain voltages whether the transistor is in saturation or not. If it is in saturation, we have solved the circuit. If it is not in saturation based on the drain current, we'll say, well, our assumption was not correct. The assumption that it was in saturation, and then we'll solve the circuit again. Alright, so this is a process we'll follow. It's kind of iterative in some sense, that because we don't know what is the region of operation, we'll make an assumption about the region, solve and check the assumption. Okay, checking is very important. We have to check the assumption is correct or not. Okay, why start with saturation? There is really no logic to it except that the saturation equation is simpler. That's all. So our equations to begin with will be simpler, and therefore we'll do the first round of solutions faster. There is no other reason for assuming saturation. Sometimes once you get used to solving circuit, you kind of figure out just by looking at it what is the region of operation. So you can use that as an assumption to solve. Also in analog circuits, most of the times, most of the transistors are in saturation. That is the other reason for, especially for analog circuits, to start with saturation. But again, must check. Checking is absolutely critical. Otherwise, we'll end up with all wrong answers if our assumption is not correct. Alright, so for our circuit, let us say we'll assume saturation. So we say, okay, we'll use this equation. Mu and Cox W by L is 4 milliamps per volt squared. So 4 divided by 2 is 2. VGS is given 0.9. The threshold voltage is given 0.4. So we'll get 0.5, 0.25 to 0.5 milliamperes. Alright, so we found the drain current. Then we find the drain voltage by Ohm's law for the resistor, because the resistor is 2 kilo ohms. So we say VD is equal to 3 minus IDRD, 3 minus 2 into 0.5, so that's 2 volts. So VD is 2 volts. And now we check, does 2 volt put the transistor in saturation? Of course, anything when the drain voltage is greater than the gate voltage, the transistor is in saturation. So our assumption is correct. So we've solved the circuit. So the answer of this circuit is the transistor is in saturation, the saturation current flowing is 0.5 milliamps and the drain voltage is 2 volts. Alright. Now, let us solve the circuit again if RD is made 10 kilo ohms. So here it was 2 kilo ohms. 2 kilo ohms. Let's make it 10 kilo ohms and solve again. Okay. Pause and solve. Okay, I continue. So RD equal to 10 kilo ohms. Again, we say, well, let me assume saturation, and we'll write the current equation in saturation, which is incidentally the same as before, because the saturation region equation does not depend on the drain voltage or the drain resistance. So this remains the same. So we say 0.5 milliamps. Now we just have to check if for RD equal to 10 kilo ohms, what happens? So we say VD is 3 minus RDID. So 3 minus 10 into 0.5 is minus 2 volts. The drain voltage is negative. Okay. Before answering the second question, let me ask the first question. Can the drain voltage be negative in this circuit? Can the drain voltage be negative in this circuit? The answer is, well, actually there are two ways of looking at it. Let's think about it. This is kind of more conceptual thinking. If this voltage, what does it say? Minus 2 volts. If this is minus 2 volts, this is 0. That means that the current has to flow from ground to the drain node in this MOSFET. Now, is this okay? Can this happen? Can this happen? It cannot happen actually. You think about why it cannot happen. One answer given is, well, current cannot flow from source to drain. That is not the correct answer, because current, a MOSFET is symmetric. In a MOSFET, current flows from N plus to N plus. Which is drain and which is source is actually decided by the voltages. So if this is minus 2 and this is 0 and current is flowing from 0 to minus 2, then one simply says that this terminal is drain and this terminal is source. Alright, this arrow is simply indicative. It need not always be so. As you may have seen in past transistor circuits in digital circuits, or so you will see probably this semester. Okay, that's not the reason. There is another reason why current cannot flow up. You think and tell me, or you figure out why. There is another rule of thumb that you keep in mind always, that if the supply rails of an electronic circuit are whatever they are, so here there are 3 volts and 0 volts, then generally speaking, I would say 99.9% of the time, any voltage in between will not go outside this range. Alright, this is just a rule of thumb. There is no theoretical proof for it. But the reason it is good to remember this rule is that as soon as you encounter a voltage outside this range, alarm bells must go on in your head. You must stop and say, oh no, I have done something wrong. Alright, not I have done something wrong, but something is wrong. This answer is not correct. Alright, minus 2 is not correct. Alright, so please remember that, and then you will be safe. Okay, so here of course what is happening is that the transistor has gone out of saturation. If the drain voltage is minus 2 volts, Vg minus Vt is 0.5, the drain voltage is lower than Vg minus Vt. So our assumption of saturation was wrong. Alright, so we say, okay, the assumption is wrong. We must solve the circuit in triode. So we write the triode region equation. So we say, okay, mu n C ox W by L is 4, 0.9, 0.4. Vd we don't know, so we say Vd by 2 into Vd. Now there are two unknowns in this. We need one more equation. What is that equation? The equation is for the resistor. We know the ID Vd for the resistor. So we say ID for the resistor is 3 minus Vd by 10. 10 is the 10 kilo ohm. So ID will be in milliamps. So incidentally, generally speaking, our dimensions will always be milliamps and kilo ohms. Alright. So we don't write kilo here. We don't, milli will write, kilo is often skipped, assuming that ID is in milli. Okay, so now we have two equations, two unknowns. We can solve. You please pause and solve. It is important to pause and solve because there is a trick, not a trick, and a question that you will come across that you need to answer before I answer it. So you pause, then you answer it, otherwise you will see my answer after this. Okay, so we solve, so I am just solving. I am not going through this, but clearly what do we see? So there is a Vd squared here, right? So we substitute for ID here, then we'll get a Vd squared, and so we get a quadratic. So we solve the quadratic, and when we solve the quadratic, we'll get Vd as possibly 0.88 volts or 0.17 volts. This Vd is either 0.88 or 0.17. Now, which is the correct answer? This is the thing to learn. We have two answers. Which is the correct answer? So let me look at each one. So you say, okay, Vd is 0.88. 0.88 puts the transistor in saturation. But we already figured out that a transistor is not in saturation. Therefore, 0.88 cannot be the right answer. Therefore, 0.17 is the right answer. 0.717, of course, put the transistor in triode. So we say the correct answer is VD is 0.17 volts, and corresponding to it, the current turns out to be 0.28 milliamps. Now, how much was the current earlier? Let us see. In saturation, the current was 0.5 milliamps. So, this is 0.28. So, the triode region current will always be less than the saturation region current if the gate voltage is fixed. Alright, when the gate voltage is fixed, if we vary RD, the drain voltage will vary. As RD is increased, the drain voltage will start dropping, and at some value, the transistor will transition from saturation to triode, and as it does, the current will start reducing with increasing RD. Alright, this is of course directly you can see from the IDVD characteristics, right? The IDVD characteristic has the highest drain current in saturation, and as VD is reduced, the drain current reduces. All right. Okay, so that I have made. Okay, another. So this is an important point, that so we'll encounter quadratic equations a lot while solving MOSFET circuits under DC conditions. We'll keep encountering them, and whenever we have quadratics, there are two possible answers, and it is a property of these circuits that always only one of the answers will be correct. So we saw here that 0.88 is not correct because it does not put the transistor in triode region. Alright, only one answer is correct. So if you find when you solve these equations that both your answers are correct, that means that you made a mistake somewhere. Alright, so again this should be a kind of alarm bell, that if you are getting both correct, don't say, I don't know which one. Both are possible. They are not possible. If both are possible, that means you have made a mistake. Please go back and check your derivation and your calculations. Okay? Alright. Let's look at the next possible simplest circuit. I'm not sure. In fact, this may be even simpler than the previous one. But anyway, this is as simple. This is called a source follower circuit, as we'll see later. Again, so same voltages, same resistor, but now we put the resistor in the source arm. Now please pause and solve this circuit. Okay, I'll continue. So for first thing we note about this circuit is that this transistor is in saturation because the drain voltage is known. We have directly connected a 3 volt to the drain. It is larger than the gate voltage. So there is no confusion here. The transistor is in saturation. So we write the saturation region equation, 2 etc. VGS minus VT. VGS is VG minus VS minus VT, and VS is not known yet. Okay, we are trying to find VS. Sometimes people write VGS as 0.9. VGS is not 0.9. VGS is 0.9 minus VS. Alright. So we have again two unknowns, one equation. The other equation comes from Ohm's law for the resistor. So if we say Vs is equal to Rs times Id, and Rs is 2, given to us 2 kilo ohms. So this is 2 Id. So we substitute both of these and we get a quadratic, and we solve the quadratic and we'll get two currents, 0.5 or 0.125, which is a correct value. Currents are always difficult to see. I'll find correct from. We find the voltages. So let's find the voltage corresponding to each of these values. So Vs is 2 times Id, so it's either 1 volt or 0.25 volts. Vs is either 1 volt or 0.25 volts. Which is a correct value? Vs cannot be 1 because Vs is 1. VGS will be negative, which means the transistor would be off, which is not possible in this circuit if you think about it. This transistor cannot be off. Okay, think about it actually. It's a good question. Why can this transistor not be off? Alright, what contradiction will this lead to if you assume an off transistor? Alright, homework. So anyway, that is not correct. So 0.25 is the correct answer. So we say Vs is 0.25 and corresponding to 0.25, the drain current is 0.125 milliamps. Alright. Okay. So this is the end of this lecture. We'll continue with more DC circuits next time and the next.